Uh, Hi there, I'm Dhruva. This is an attempt. I'm going through the Jack scaling book. So I I had recently read somewhere. I believe this was in one of the blogs from Brad Feinberg. So he works at DeepMind, Google DeepMind, and I saw him mentioning the Jack scaling book, and that whoever solved the exercises from Jack scaling book would be he would interview them, and he would give them a chance to interview a DeepMind. And I heard of the Jack scaling book before. I think it was released back in 2024 or something, or 2025 maybe. Might be wrong there, but 2025 in February, and I'd seen. I'd sort of gone through the part 0, part 1 for it at the time, but I never managed to complete it. So here's an attempt at going through the Jack scaling exercises one by one, and the theory as well. So this is going to be like a multi-part series that I'm going to try to do, and throughout this journey I'm going to try to learn myself as well, because I haven't. So there's going to be sort of part learning, there's part teaching, and through teaching I hope I'll learn something new. So here goes. Right? So part 0 is basically a sort of introduction to what this the book is going to be about, or what the blog series is going to be about. So the authors to this, so the guys who spearheaded this thing were, one of them was Sholto. He's pretty famous now. I believe he works at Anthropic, and some other guys like Rainer Pope and all these guys. So the ones who sort of spearheaded this. Okay, so that's that. I think I'm going to try to put this lecture in really simple words so that someone with a basic computer science background, and maybe someone who has even a very rough basic idea of machine learning, and someone who's even just heard of transformers will be able to follow through, and just some basic maths. So I'm going to start by explaining the transformers architecture. Because the introduction actually mentions the 2017 attention is already paper by Vaswani et al. So here goes. So what is attention? So attention is, say there is a line, there are multiple tokens in a sentence. So my name is now. I have to flip this but so in this sentence, how does a model that has no understanding of natural language inherently know that this token is sort of related to this token, and this token, that the first token is related to the second token, and how does it know that Dhruva is related to this token here, D? And then how does it make these connections across the sentence? And how is it able to hold the relevant context throughout even just one sentence? So yeah, I mean, this is the sort of basis of how attention, of how transformers work, of how attention works. So I'll get into the technicals right now, and then maybe I'll try to sort of put it into really simple words. Right, even like I said, a beginner could understand. So I'll just draw out the architecture maybe first. So I'll draw it out part by part. So what does this say? And so the model obviously cannot understand, like I gave the example of like, just say take any word. Like the model cannot understand that at face value. So I mean, there has to be a way to feed these models in their own language, right? In a different language. So what is that language? So that language is the simple vectors and simple, just integers in a vector, right? Now, so these inputs are just words. So these inputs are words. So when you talk to let's say when you talk to ChatGPT, or when you talk to Claude, or when you talk to any other AI model out there, your input is words, is tokens, right? Is natural language. But like I said, the model obviously cannot understand natural language at face value. It cannot take it at face value. So it converts that into something called input embeddings. Now, what are input embeddings? It sounds like a very complex term, but it is actually pretty simple. Like I said, it's just vectors. It's a set of vectors. Now, someone might ask, how are these tokens, just natural language, converted to vectors? Right? So there are two things involved here. Right? So one is basically encoding. Now, in this specific, since we're going through the transformers architecture, positional encoding is a specific type of encoder where the something called rotary embeddings are used. Again, I'm using very complex terms, but I promise I'll come back to explain these terms in very simple words later on down the line. So, so input embeddings. Right? So input embeddings. How does this conversion take place? Now, there's something called a byte level encoder, right? So this started with something called BPEs. It was created by Google, I believe, back in the day. And so what these byte level encoders basically do is each word, let's say each token, let's say I name you. Now, this complete token doesn't actually have any meaning to a model, right? So this is sort of broken down. I mean, this might be sort of taken as one complete token for a model, or it could also be broken down, right, into two separate tokens, NA and ME. Right. Now, at the byte level encoder, I mean, at that level, at the encoder level, what is done is these sub-tokens or these tokens are assigned specific integer values. So I'm going to keep it really simple for now. So I'll just take integers. So it could be, let's say this, some number for now, it's just 2. This is not how it actually happens for transformers, but yeah, just for simplicity. So let's say the number 2, right? So NA is assigned the number 2, and ME is assigned something else, number 3, let's say. Okay. Now, so this is how it's basically broken down. These are assigned some at a character level. Each character is assigned a specific integer value, let's say, a value, right? And so all of this together, it forms a vector, right? So it could be, I'm just going to take some variable x1, x2, x3. So this is a sort of form of these input embeddings. Now, the conversion from inputs, I mean, there are multiple ways to sort of convert these inputs to these embeddings. Like in the case of transformer again, I said positional encodings. Right? Now, positional encodings is just one more type of these character level encoders. So specifically in transformers, something called sinusoidal encodings are used. So sinusoidal encodings are basically sine and cosine functions of sine and cosine functions basically. Now I'll just write the equation down maybe. This is so 2i is basically the index, right? So let's say there's a sentence like to the example of my name is as I said. Now I is basically the index of each token. Now again, like I said, it could be that my complete leaf is not one token, it's broken down into M and Y, but that depends on the specifics of the encoder that is used. So if my name is D, right? This is 0, 1, 2, these are the indexes in the sequence. Now I is just these indexes, and sine is the sine function. So position y tells it to y by d model. Now what is d model? Right? D model is just the dimension of the model. So we'll come to this later. But yeah, just keep this in mind for later on maybe. So this is the dimension of the model, and we'll keep this for later. Now this is what the function form looks like when converting these inputs into these embeddings using something called sinusoidal encoding or positional encoding. Right now, let's say obviously in a sentence there is 2i, meaning the even indexes, and 2i plus 1, the odd indexes, right? Now 2i plus 1 is the cosine of the same function basically. So it's a PE of 2i plus 1, and you can just use the same, so instead of sine I just use cosine. So this is a cos of, let's say this is f of x here, I'll just name this f of x here. Y plus 1 by dimension of 1. So this is for the odd, the tokens at the odd indexes. So this is it with embeddings. So this is take one.